Going on, guys, let's do this problem right here. The question is asking determine if A is diagonalizable. So let's see how we can find it. So we know to something to be diagonalizable, it has to have algebraic multiplication and geometric multiplication. Both should be equal numbers. So let's check whether they are equal. So from this one, how do I check this one? So in this case, the eigenvalues are easy to find because it's an upper triangle. So basically the diagonals give us the eigenvalues. So here we have lambda is equal to 1 and lambda is equal to 4. However, this 1 is going to be algebraic multiplication of 2 because it's repeating twice, right? So therefore it's algebraic multiplication of 2. So now we have to check geometric multiplication. How do I check geometric multiplication? Basically it's the free variables. So number of free variables gonna tell you the geometric multiplication. So let's see. So in this case, so in order to do that, I have to first go and see what's the vector of this one is going to look like. So to find the vector, I have to set up this equation. The usual formula we do is a minus lambda I. We set this one into null space and find the vectors. That's how we do. And in this case, what I'm going to do, I'm going to copy this matrix. So 1 1 0 0 1 1 and 0 0 4. So if you multiply lambda by identity is going to be 1 0 0 0 1 0 0 0 1. If you multiply, it only multiply the diagonals, and if you subtract from A, so it's going to subtract something like this. So minus I directly, so this is 1 minus lambda, then 4 minus lambda. So let's copy this one more time. So in this case, I'm going to apply lambda is equal to 1. Let's check whether it has two free. In order to be diagonalizable, it has to have two free variable. Then only it will be diagonalizable, because algebraic multiplication is 2. So in order to be diagonalizable, the geometric multiplication should be equal to 2. So let's check whether it has two free variables. That will tell us everything. So in this case, it's going to be 1 minus 1, 1 0, 0, 1 minus 1, 1, then 0 0 4 minus 1. So if I so this is equal to 0 0 0 0 0 0. We are setting this one into null space. So I continue in the other side. Here it's going to be 0 and 1 0 and 0 0 1 0 0 3 equal to 0 0 0. Now I have to do the Gauss Jordan. So if I do the Gauss Jordan, I can simply eliminate this one by multiplying this one by -3 and adding this one. So it's going to be 0 1 0 0 0 1 0 0 0. So this is going to be the null space of this one. And if you see, this is a free variable because this one doesn't have any leading one. So this is a free variable. This is not a free variable. This is also not a free variable because both have leading one. So we know the free variable is 1. Therefore, from now on, we know that this is not diagonalizable, because since free variable is 1, the geometric multiplication of this one is equal to 1. Geometric multiplication is 1. Therefore, this is not diagonalizable. So the answer for the first question is no. And the second question is asking, if A is 3 by 3 matrix with eigenvalues 2, 3, 1, find trace of A inverse. Trace is basically addition of these diagonals. So we know if A is given, we can find the trace like simply adding this one. So how to find A inverse? So they have given the eigenvalues for A. So to find the A inverse, there's a property of eigenvalues says that to find the A inverse, we can simply find the trace of A inverse. We can simply take the eigenvalues of A and put it as lambda inverse. Like if you find the lambda inverse and add them together, that's going to give the trace of A inverse. So that's one of the property. So it's going to be, therefore this is going to be 1 over 2 plus 1 over 3 plus 1 over 1. That's going to give us the trace of A inverse. So in this case, let's calculate this one. So we know this common denominator is going to be 6, and here is going to be 3 plus 2 plus 6. If I add them together, I will get 11 over 6, and this is the answer for the trace. This is the trace of A inverse, and that's how we do these questions. And I hope you guys like this video. See you next time.